Hello, everyone, and welcome to another episode of Eyes on Earth. We're a podcast that focuses on our ever-changing planet and on the people here at EROS and across the globe who use remote sensing to monitor and study the health of Earth. I'm your host, John Holt. We talk a lot about the land on this show because land remote sensing is the focus of the USGS EROS Center. But the Earth observation data archived here have plenty of value to the study of aquatic ecosystems. Landsat satellites can capture harmful algal blooms, for example. Spaceborne sensors can also record land surface temperatures, and that includes water surfaces. Two of today's guests are exploring how to fuse those remote sensing measurements with readings collected on the water to better understand the daytime variations in temperature in California's San Francisco estuary and Sacramento-San Joaquin River Delta. The area is home to the endangered Delta smelt, a 4-inch fish with a 1-year lifespan that smells like cucumbers and feeds on plankton. Cute, right? But they're a big deal. They only live in the Delta and they're an indicator species, meaning that their health tells us a lot about the health of the ecosystem they inhabit. PhD candidate Becca Gustine was the lead author on a study that showed how Landsat and a sensor called ECOSTRESS can be used to measure water temperatures in the Delta. ECOSTRESS is affixed to the International Space Station, and its data are archived at NASA's Land Processes Distributed Active Archive Center, or LPDAAC, which is located at EROS. Becca is now working on a follow-up study with another researcher at NASA's Jet Propulsion Laboratory, Dr. Cassie Nichols, and we're excited to hear about it from both of them. Also joining us is Dr. Shruti Khanna, a senior environmental scientist for the California Department of Fish and Wildlife. Shruti has spent years using remote sensing data to study aquatic invasive species and the effectiveness of management practices in the Delta. Becca, Cassie, Shruti, welcome to Eyes on Earth.
Thanks for having us.
Thank you.
Thanks, John.
Let's get started by talking about the use of remote sensing to track water temperature kind of in general. What are the advantages, disadvantages, and what are some of the caveats we need to think about with space-based measurements?
So remote sensing is awesome because it has such a large coverage spatially. You're not just zooming into one single point or a subset of an area like you usually have to do with ground-based measurements, like gauges. You can literally see everything untrapped from space. It offers access to places and locations that can't always be reached on the ground. A lot of the times it can be pretty hard going out with ground surveys to study wetland ecosystems like we do with water temperature. And honestly, it's just really cool to say that you can get water temperature from space. Like you just go around telling that to people and they're like, wow. But there are some drawbacks. Water temperature measured from an instrument like ECOSTRESS takes the surface water temperature instead of the deeper water in the water column. And obviously fish don't just stay at the surface. So if we're looking at species and how they react to the warmer temperatures, we can't just say, oh yeah, let's just look at that water temperature at the top. But we can derive relationships between the surface water and these temperatures at depth, which is called bulk water temperature, which Becca will probably talk about more later. But then also another just general drawback to some remote sensing instruments, clouds. Clouds can really get in the way. If there's a cloud below your sensor, that means, oh, whoops, we don't have data in that region. But that's okay. It doesn't happen all the time. And then another caveat for remote sensing is we can't always get the daily measurements like you might be able to on the ground. ECOSTRESS, it's been up there since 2018, and it has a better revisit time in the Delta that we're looking into. It's like a 1 to 3 day revisit. In the US, it's 1 to 7 days to come back to that same location. There are really pros and cons for sure, but overall remote sensing is readily available, it's free, and can help researchers and water resources managers really just get the bigger picture of what's happening in our study areas.
Now, before we dig into some of the research that you're doing, let's talk about the study area in general. Why is it so important to understand the dynamics of the Delta? Who are the stakeholders here, and what are the pressure points?
I can take that. This is Shruti. I've been working in the Delta since 2004. It's kind of my playground. And the Delta is one of the most invaded and the most modified estuaries in the world. It is a gateway for invasive species into the state, but it is also the critical water conveyance pathway for water to go from Northern California to Central and Southern California for both agriculture and for drinking water for urban centers. It has been reclaimed to a huge extent, and so the marshland that used to cover the Delta is down to a fraction of its historic extent. And the entire hydrology today is different than from its historical hydrology, in which its animals and fishes and everything has evolved. For an added problem, California is known for its water wars, right? So there are a diverse number of stakeholders in the Delta, including farmers, water users, contractors, and regulators of that water, fishermen, and natural resource conservation and restoration managers. This brings in so many different missions on the side of all of these stakeholders that there are a lot of pressure points. And in a nutshell, it can be called as the tug of war between water delivery and ecosystem health. The Delta ecosystem has been in decline due to many reasons, including these changes that have happened over time to its hydrology due to invasions of clams and submerged and floating aquatic plants.
So can we talk about that just a little bit? I mean, we talked about the water flowing north to south and all those pressure points, but that's kind of interesting. How are invasive species a problem? Why can't we just live and let live with these invasive species?
It's amazing what a tremendous amount of change these invasive species have caused to the Delta ecosystem. The clams, for example, came in, and clams are filter feeders. So they just sit there on the bottom and they are, eating up all of the phytoplankton, the single-celled green algae that is being produced in the water, which is a very important resource for two things. One is fish larvae, and the other is there are smaller organisms that eat that phytoplankton, which are then eaten by the fish. Think of it as this food chain in which the bottom of the food chain started to disappear because of the clams. This led to a large extent to the crash of Delta smelt and longfin smelt, which are endemic endangered fishes in the Delta. That's just the clams. But then you have these aquatic vegetation species that also do a vast amount of harm. They have brought down the turbidity in the Delta. And again, these tiny little fish, these pelagic fish, the smelt, they like to hide in muddy waters. That's how they escape their predators. And so by the water getting clearer, it is less conducive to their survival. At the same time, the submerged aquatic mats in the water offer very nice hiding places to their predators. And so those predators become more effective at hunting them. Things like that have caused this cascading effect on the endangered species in the Delta.
Let's talk about that now just a little bit more. Why is Delta smelt such an important species to monitor? Obviously, it's an endangered species, and you're getting into a little bit of that. Why is this such an important species?
Yeah, it's endangered, right? But it's also an indicator species. So if they're decreasing in number because of the decrease in phytoplankton and food sources and different things like that, it really largely reflects bigger issues in the region. For example, warming temperatures due to climate change. These fish species, they can't handle that abrupt change so quickly. And so the ecosystem shifts. And so we're looking into Delta smelt specifically because it's so abundant in the literature. So many people have been looking at Delta smelt for years, it seems like. And so there's a very big base to go off on. And so we can study Delta smelt, but also add in other species that are important, like salmon. And it'll tell us more about the region.
It's the biggest little fish in the Delta.
Exactly.
Shruti, you work for the state of California. Tell us a little bit about how you've used remote sensing to study this area.
So I've been doing research in the Delta since my early PhD years in 2004, and I started looking at floating invasive species. My PhD was on the impact of water hyacinth, and I've been looking at since then not only at how these invasive species affect the Delta ecosystem, but also how management or the efforts to control these species have affected the Delta and how effective those efforts have been. I have been looking at the control program for controlling both submerged and floating species. And one of the major issues that happens there is because the Delta is a tidal ecosystem, the water is constantly moving back and forth. Herbicides that are sprayed on these invasive species do not stay in one place. They move around, and so they aren't as effective. We were also trying to figure out how to make the control program more effective. What do we need to do? What is the minimum amount of efficacy that we want to achieve, and how do we achieve that? What is the concentration of the herbicides that should be in there? There have been efforts to prevent intrusion of salinity into the Delta during drought years. For example, using the drought barrier, which is this huge stone bridge that they build across one of the major inlets into the Delta from the bay. And that prevents tidal water from bringing in salty water during times of drought. So we looked at the effectiveness of the drought barrier, and for sure it is effective in preventing salinity intrusion, but it also stopped tidal pumping into the delta. You've basically put in a barrier to water coming in and out. That led to an increase in submerged aquatic species, which really like slow-moving lake-like water environments. It had unintended consequences.
Using remote sensing, you were able to tease out some of the things that you didn't want from this management practice.
Exactly. So
right.
They were very concerned about, changing the amount of submerged vegetation. There's a big flooded area down there called Frank's Tract, which used to be an old island that the levees breached, and now it's like a lake. And that entire lake now is full of submerged aquatic vegetation, which used to have less of that because of all the tidal pumping that used to go through that region. And because we have been mapping the delta using remote sensing imagery every single year, we are able to see what the condition used to be like pre-barrier and post-barrier.
That's interesting. And that should bring us back to Becca and Cassie, because you're using remote sensing to measure water temperatures. You're looking at that metric, but first you had to figure out whether it would work, as I understand it, for people like Shruti to use in their work. So tell us about the research that you've done.
Yeah, this is Becca. We were seeking to use ECOSTRESS, Landsat, and an extensive in situ network of sensors in the Bay Delta to try to better understand how these different temperature data sets went together.
So in situ, you mean in the water?
Yes.
Measurements.
The ground-based sensors that are actually measuring water temperature every 15 minutes to every hour. So we wanted to use a suite of temperature measurements to see if we could better understand how they go together, how and where we can use Landsat versus ECOSTRESS versus the in situ measurements, given the trade-offs that have been mentioned earlier about in situ versus remote sensing data sets. We wanted to get a fuller, more complete understanding of how water temperatures were changing both at the surface and at depth over time, both diurnally and over the ECOSTRESS record. We used ECOSTRESS because it has that diurnal overpass cycle to create a simple harmonic regression model using that quantified skin effect. And when I say skin effect, I mean the difference between the water temperature at the surface and the water temperature about a meter below the surface. So what we found with this research is that we can create a simple harmonic regression and have it perform, as well as other physically based models that have been calibrated for the area, to create these bulk water temperature maps. And that Landsat, ECOSTRESS, in situ measurements all really are complementary. So we can use them to better understand how things are changing in the Bay Delta, both over time and over space.
So with a little math magic, the harmonic regression, you are able to figure out that you can, in fact, do this over wide areas and not just get the single measurement, because with ECOSTRESS, you get multiple measurements a day, as I understand it. You can see when that diurnal is what you're talking about, within the day, what the changes might be. You're able to pull this off and it's reliable.
With ECOSTRESS, during those warmer months when we're most interested in thermal habitats, we get an overpass in the Bay Delta about every 1 to 3 days, and they occur at different times of the day every time. So we have overpasses in the morning, in the evening, in the afternoon. So we can get a better understanding of what the average temperatures look like in the morning versus in the afternoon. And the afternoon is mainly when we're concerned about that thermal habitat. And so, yes, having that temporal range in temperature measurements allowed us to create this model to pretty much show the diurnal curve that we were seeing with the bulk water measurements.
But you could do it over a wide scale, obviously.
We could do it over a much wider scale. And with that, we're now starting to look into using those bulk water temperature maps to investigate thermal habitat suitability for the Delta smelt and other species in the Bay Delta.
Is there anything else about ECOSTRESS that makes it unique compared to something like, say, a MODIS instrument that would get one image every day? Is there anything else that makes it unique and useful?
The combination of measurements that we used for this research provide a variety of different spatial and temporal scales and measurements that we were able to combine in what I find is an interesting way. ECOSTRESS, like we said, has that diurnal overpass, and the temporal frequency is much higher than a lot of the other satellites that have been launched. ECOSTRESS, with having that fine temporal scale, still has a relatively fine spatial scale, being at 70-meter resolution, whereas Landsat has a 30-meter resolution. So there were trade-offs in the data, and we had to do some manipulation to make sure everything was on the right spatial scale and temporal scale. But the major benefit is that remote sensing has a more continuous and much wider spatial range than the in-situ measurements. So while the in-situ measurements were measuring exactly what we were interested in, the bulk water temperature, it was only in sparse locations. There are a lot of sensors throughout the Bay Delta, but only a handful were really relevant for this study and for the thermal habitat study that we're investigating because they represented the Delta smelt conditions better. And so we had to use a handful of sensors and combine that with the two different remote sensing data sets to try to piece together a story about how temperature was changing at depth. Cassie can probably talk about how our next paper is going to start leveraging those relationships that we found, as well as the model, to begin looking into habitat suitability and some of the things that we're looking at to inform management decisions. First step, we just want to observe what's going on, not just station by station, but at the grander scale, like Becca just talked about, finer spatial resolution, but we can see all of it, not just on the ground-based temperatures. And that's been validated because of her past paper. So now we want to look at maybe even the fluctuation rates between suitable and unsuitable habitat. How fast are regions or water pockets becoming unsuitable versus suitable, shifting from day to night? Because at nighttime, it's pretty suitable everywhere. It's cooler temperatures, right? But during the day, midday, when the sun's beating down really hot, that temperature in the water gets pretty toasty. And so we want to see, okay, what species are in danger? What are the thresholds? Because there needs to be specific temperature thresholds for fish species to spawn and to even survive, honestly. And so we want to look at which ones are in danger. I mean, we know we have a good handle on which are in danger, but we also want to look into dispersal ranges. Like, do they have time to swim away? We have this wider grasp and look from above to see, like, okay, which regions, which pockets are pretty bad? And are there other regions right next door that they can disperse to readily? So that's really what we're aiming for this next study.
You haven't used ECOSTRESS data at this point, as I understand it, but I'm interested to hear how this kind of data and this kind of work that Cassie and Becca are doing, it's my understanding you have to pay for the remote sensing data, at least some of the remote sensing data that you use. Is that right? And here we have ECOSTRESS is free and open to everybody. How would this be useful for you, or would it be?
Yes, we pay for the data that we collect over the Delta. In fact, the airborne hyperspectral data that we have been collecting costs us anywhere from $100,000 to $200,000 per year. It's definitely costly, and that's definitely an issue. And in recent years, we have started using these open data that are available, like Sentinel-1 and 2, to kind of do floodplain monitoring, to monitor these invasive species also to some extent. But I'm really excited about ECOSTRESS in particular, because, we've been trying in recent years to build occupancy models for invasive species to be able to predict where they will spread with climate change and with changing conditions in the Delta. One of the missing things in there has been temperature. We know that temperature affects how Aegeria densa, for example, a submerged invasive in the Delta, grows. In fact, at very high temperatures, Aegeria densa also doesn't grow as well. And then we have the floating species are particularly vulnerable to frost. So there are these conditions which, if we had this kind of a 2D map that Cassie and Rebecca have been building, that adds one more layer to things that we are already looking at, like water speed, water depth, things like that. And so you add temperature in there, you get a much more complete picture of what kind of a niche these species like to come into. And so you can actually predict what will happen as temperatures change. That's what excites me, is I would like to take my work in that direction and build better predictive models.
And again, Cassie and Becca will not charge you $200,000 for this
yes.
additional metric that you would now have access to for your models.
This movement towards open data, open science has been great for researchers like us, right? Because it has fostered this kind of collaborative effort.
What are some closing thoughts you'd like to leave our listeners with? Do you want to talk about open data or invasive species? What are the big points that you want to leave with the folks that are listening today?
For one thing, with all of these new sensors on board, especially different kinds of information with, temperature coming from one side and multispectral data, the kind that allows us to classify these species in the Delta, And all of these different kinds of data models, we are able to combine these very diverse kinds of information and take our studies where they have never gone before. That is definitely a big advantage with these things. What this helps us do is to build better predictive models, not only of how the management actions that are being taken affect the delta, but how will potential management actions affect what's going on. That is where I see a lot of value to this kind of movement.
I just wanted to promote remote sensing in general because it is this free and publicly available data set and it covers a wide spatial range. And so you're really only limited by your imagination and curiosity with what you can do with these tools. And it's been really fun to dig into it and the networks, the relationships that we can build with managers to try to make sure that our research at JPL is useful to them.
Yeah, I completely agree with that. We as researchers, it's our job to notice things, but it's really only helpful if we get that information that we notice to the right people. And so I love to have different people from different areas of expertise in the room so that we can bridge the gap and help each other learn and take action.
Becca and Cassie's work, in fact, is a very great example of that because they have been working with state scientists and federal scientists, people who are actually managing the land and doing the kind of research that we need to be able to better manage it.
We've been talking to Becca Gustine, Cassie Nichols, and Shruti Khanna about remote sensing and aquatic ecosystems. Thank you all so much for joining us.
Thanks, John. That was great.
Thank you, everyone.
Thanks, John.
And thank you to the listeners as well. You can find all our shows at usgs.gov/EROS. That's usgs.gov/EROS. You can also subscribe on Google Podcasts. This podcast is a product of the U.S. Geological Survey, Department of Interior. They really smell like cucumbers?
Yeah,
I have
they
no
do.
idea. They do?
They do. They actually do.
That shocked me when I first read that. I told everybody I knew.